So welcome back to physics online session. So in last videos we had discussed on capacitance of parallel plate capacitor. So in that capacitance of parallel plate capacitor, so we discussed the concept related to capacitance of parallel plate capacitor without dielectrics, or in the sense areas act as a dielectrics. So in second thing, so if that dielectric medium is completely filled between the plate of the capacitor, what about its capacitance value, whether it will increase or decrease, I come to know. For example, so in case of that parallel plate, let me take that two plate here. So between these two plates, so there exists a certain kind of separation. So areas act as a dielectric medium. So in this situation, so capacitance value C naught is equal to epsilon naught into A divided by D. So without dielectrics, or areas act as a dielectrics, or in the sense if that between these two plates, if dielectric medium is completely filled, so then its value changes as C is equal to K into C naught. It means that capacitance value is increases after placing the dielectric medium. So I shall rewrite it here, this equation as K into epsilon naught A divided by D. So now in that another situation, so I will consider the dielectric medium. So that dielectric medium is partially filled. So if that dielectric medium is partially filled between the plate of the capacitor, so for example, so this thickness I will take it as a T here, and distance between the plate I will take it as a D here. Now what will be its capacitance value? C is equal to epsilon naught into A divided by D minus of T plus of T by K here, or in the sense another form I will rewrite here, D minus of T 1 minus of 1 by K. So these are all the equations related to capacitance of parallel plate capacitor. So now already I got that information about capacitor. So basically capacitor in the sense it is a device which is used to store large quantity of charges at low potential. So that device I will name it as a capacitors here. So if these capacitors I will arrange in a series combination, or otherwise I will arrange in a parallel combination. So first I would like to understand what is series combination and what is a parallel combination. After that we were going to be learn about that what about the effective capacitance if two or more capacitors are arranged in a series combination, or two or more capacitors are arranged in a parallel combination. So let me begin with the concept of grouping of capacitance. So in case of grouping of capacitance, series grouping as well as parallel grouping is there. So let me understand one by one. So let me start with the concept grouping of capacitors. So for theory as well as competitive examination corner, so this aspect is very much important. Grouping of capacitor. So in case of that grouping of capacitors, so I will take series grouping as well as parallel grouping or series combination. So first one I would like to understand series combination. So in generally what do you mean by that series combination or series connection? For example, I am providing these two or three pen I will provide you. So how to arrange these three pen are in series combination. So series combination means end to end connection. So for example, this is one pen. So I am going to be connect this one to another one, this one to another one, like that. So end to end connection I will name it as a series combination. So in generally that series connection, how will you make that series connection? One after the other. So in the other sense I can say that one after the other. Such kind of combination I will take it as a series combination. Now I will consider the two or more capacitors, and my intention is to arrange these capacitors are in series combination. So if I arrange the capacitors in series combination, that effective capacitance or total capacitance in series grouping, whether it is less than the individual value or so more than the individual value I want to determine. So in order to understand such thing, so I want to give that mathematical approach for that series combination of capacitors. So in case of that capacitors, so I said that it consists of two plates, one is positive and another one is negative here. So for example, this is first plate and this is positive plate and this is negative plate, and let me consider that another plate here. So another capacitance, So that capacitance is C2 here. So in this capacitor also it consists of positive and negative plate. So I am having two capacitors. So I will connect that these capacitors in a series combination. So how will you make that series combination? So negative plate of the first capacitor. So listen here, negative plate of the first capacitor is connected to the positive plate of the second capacitor. So listen here, how will you make that series connection here? Negative plate of the first capacitor is connected to positive plate of the second capacitor. In the similar manner, so another one more capacitor I will consider, C3 here. So this is positive and this is negative here, like that. So in case of that series combination, end to end connection, how will you make that end to end connection? Negative plate of one capacitor is connected to positive plate of the other capacitor. So such kind of combination I will take it as a series connection here. So in case of this series connection, so at the end I will give that battery connection here. So positive and negative. So potential difference is V amount. So look at here. So I consider two capacitors here, C1 and C2. These two capacitors I arranged in a series combination. Now let me understand that in case of that series combination of that capacitance, which of the quantity will be remains the same. So I am having connecting formula, C is equal to Q by V. Out of these two terms, so charge and potential, in case of series combination, which of the quantity will be remain same I need to understand, whether charge will remain same or potential difference I need to understand. So for that purpose, look at here. So from this battery, charges are moving here. Okay. So now let me understand that what about the charge in the first capacitor and second capacitor. So let me pause for certain extent here. So for example, instead of these two capacitor, let me take that two pipe here, water pipe. So having different diameter. For example, so this diameter is 5 meter square I will consider, and another one more pipe I will take that. So this is having that diameter, diameter is 10 meter here, this diameter is 5 meter here. So now 1 liter of water I will make it to allow into this pipe here. So 1 liter quantity of water I will make it to allow here. That 1 liter of water is enter into the first pipe and the same quantity of 1 liter of water is enter into the second pipe here. It means that that quantity of water is remains same in first pipe and as well as in the second pipe here. So look at here. So if I take that 1 liter of water here, that 1 liter of water I am passing through that of first pipe and second pipe here. Even though these pipe having the different diameter, that quantity of water will flow into that first pipe and as well as in the second pipe is remain same. Here also 1 liter water will get flow. So this water will flows to that of second pipe. So here also 1 liter of water is present, or you may interchange here. So for example, you may arrange this pipe as a first one and another pipe you may take it in a second one. So again the same thing, if you pour that 1 liter of water in this pipe, so 1 liter of water is enter into this first pipe and same 1 liter of water will enter into the second pipe. It means that quantity of water is remain same in these two pipe. In the similar aspect, so charges are moving from that one capacitor to another capacitor. So if you connect that capacitors are in series combination, means charge will be remains same. The quantity of charge flows to that first capacitor, the same quantity of charge will flows through the second capacitor. It means that in case of that series combination of the capacitors, that charge will be remains same here. So did you get my point here? So in case of that series combination, I want to understand that which quantity will be remains same in a series combination. So what's the answer for that? In case of series combination, charge will be remains same here. So in case of that series combination, that quantity of charge in the first capacitor is equal to quantity of charge in the second capacitor. Why? Because that same amount of charge will flows through that of first as well as second capacitor, whatever its value. For example, if it is 5 microfarad and it is 10 microfarad. So in case of these two capacitors having the different value here, so if you connect these two capacitors in a series combination, the amount of charge will be remains same here. For example, in that first capacitor. So for example, that first capacitor will allows that 10 coulomb of charge. So that same 10 coulomb of charge will flows through that of second capacitor. So look at here. So C is equal to Q by V here. So for example, so here that from the first capacitor, if 10 coulomb of charge will get flow, means if from the second capacitor also same 10 coulomb of charge will get enter here. Or you may take that first 10 microfarad. So first you may consider that C1 as a 10 microfarad and C2 as a 5 microfarad here. Okay. So in this situation, for example, so capacitance is directly proportional to charge here. So for example, in that first capacitor, for example, if 5 coulomb of charge will flows through the first capacitor, the same quantity of charge will flows through the second capacitor or whatever. So if that capacitance is directly proportional to charge here, so Q is proportional to, or that Q is proportional to V, that Q is equal to C into V. In last class we discussed that. So shall I rearrange here? C is equal to Q by V here. So it means that, so in case of that series combination, the quantity of charge will be remains same here. For example, so one capacitor is 5 microfarad, so it will block a certain kind of charge, you may consider that. So out of 20 coulomb of charge, so it will block that 5 coulomb of charge, it will allow 15 coulomb of charge. The same 15 coulomb of charge will allow into that second capacitor here, and the thing will be same. Or otherwise, if you take the 10 microfarad here, so 10 microfarad will allow that 18 coulomb of charge here. That same 18 coulomb of charge will allow into the second capacitor. In the sense, in case of that series combination, that charge will be remains same, I said. So if that charge will be remains same, means so total potential difference is equal to sum of the individuals. So hope you are understanding here. In case of that series combination of the capacitors, which of the quantity will be remains same here? Charge will be remains same. So did you get my point here? In case of that series combination, which quantity will be remain same here? Charge will be remains same. So let me derive an expression here. Consider a capacitor of capacitance. Consider a capacitor of capacitance C1 and C2 are connected in series combination. What is that series connection here? So negative plate of first capacitor is connected to positive plate of the second capacitor. Then in series combination, charge is remains same. Charge is remains same. So that is Q1 it is equal to Q2, or generally I will take it as a Q here. So in case of series combination, charge is remains same. Now if these two capacitors are connected in a series combination, what about its potential difference I need to find out here. So total potential difference is V amount here. So total potential difference is equal to sum of its individuals. So V is equal to V1 plus of V2 here. So now let me consider that total potential difference. Total potential difference is equal to sum of its individual. So total potential difference is equal to sum of its individuals. So I will take that V is equal to V1 plus of V2. So shall I take it here? So V is equal to what? V is equal to V1 plus of V2 here. So now let me consider that generalized formula for capacitance. So we know that C is equal to Q by V here. So shall I rearrange this equation here? So C1 is equal to what? So Q1 by V1 here. and so this equation I will rearrange here. So V1 is equal to what? So V1 is equal to, shall I take this one as a Q1 by C1 here? In the similar aspect, C2 is equal to Q2 by V2 here. Shall I take that V2 is equal to Q2 by C2 here? I got that V1 and V2 value. Let me take this as a equation 3 here. So I will substitute that equation 3 value in equation 2 here. So I will substitute that equation 3 value in equation 2. So V is equal to, so V1 means what? So V1 is equal to what? So instead of V1 I will take it as a Q1 by C1 plus of, instead of that V2 I will take it as a Q2 by C2 here, Q2 by C2, where in case of series combination charge is remains same I said. So charge is remains same means Q by C1 plus of Q by C2, where, or from equation 1, from equation 1 we can rewrite as, okay, so I will rewrite this equation. So V is equal to what? So Q by C1 plus of Q by C2. So Q is equal to what? So Q I will take it as a common here, 1 by C1 plus of 1 by C2 here. So what's the equation here? So V is equal to Q into 1 by C1 plus of 1 by C2 here. So in case of that V, so C1 is equal to Q1 by V1 I said. So C2 is equal to what? Q2 by V2 I consider. In the similar aspect, V is equal to, shall I take this equation as a C equal to, sorry, V is equal to Q by C here. So look at here. So I would like to write this equation as a first one. C is equal to Q by V, or V is equal to Q by C here. So C is equal to what? C is equal to Q by V. V is equal to what? Q by C here. So effective capacitance in series combination I said. So just I will write this equation as a Q divided by C of S. So wherever V is there, so what shall I take it here? So Q divided by C of S. Q divided by C of S. So hope you are understanding here. Q divided by C of S. Q divided by C of S. So the term Q will get cancelled out here. So if it is getting cancelled means what will be the final equation I will get it here? 1 by C of S is equal to 1 by C1 plus of 1 by C2. So hope you are understanding here. So look at here. In case of that series combination, so I said that if that series combination means end-to-end connection, or negative terminal of first plate is connected to positive terminal of the other plate. So in these situations, that which quantity will be remain same? In case of series combination, charge will be remains same. So total potential difference is equal to sum of the individual I said. So V is equal to V1 plus of V2 here. So in generally I know the equation for capacitance. So C is equal to Q by V here. So V is equal to, I will rearrange as a Q divided by C of S. So wherever V is there, so just I will take it as a Q divided by C of S here. So V1 is there. So wherever V1 is there, so I will take it as a Q1 by C1 here, plus wherever V2 is there, so just I will take it as a Q2 by C2 here. So in case of that series combination, charge is remain same I said. Instead of Q1 I will take it as a Q, instead of Q2 I will take it as a Q here. So here also Q term is there left side. So Q term will getting cancelled out. 1 by C of S is equal to 1 by C1 plus 1 by C2 here. Or if you take that LCM, in other way I can write this equation as C of S is equal to C1 into C2 divided by C1 plus of C2. So if you take that LCM, what will be the value of effective capacitance if the two capacitors are connected in series combination? So C of S is equal to C1 into C2 divided by C1 plus of C2 here. So from this equation I can conclude that effective capacitance is greater than the individual, or whether it is less than that individual here. So for example, let me take that two capacitors value here. So one is 2 microfarad and another one is, so C2 value So C2 value, another one is 3 microfarad. So if two capacitors are connected in series combination, whether that effective capacitance, effective means total here, effective capacitance is greater than the individual or less than the individual, I need to cross check here. So for that purpose, so hope you are understanding these derivations. So I want to calculate that effective capacitance is less than the individual or more than the individual. So what is the connecting formula I have here? So C of S is equal to C1 into C2 divided by C1 plus of C2. These two capacitors are arranged in a series combination. One is 2 microfarad, another one is 3 microfarad. So 6 by 5 here. So this value is less than that of 2 and less than that of 3 here. So in case of that series combination, so this one is farad. So in case of that series combination, effective capacitance is less than that of individual. So 6 by 5 is less than that of 2 here. So I can consider in case of series combination, effective capacitance is always less than that of individual here. So for that purpose, another example, let me take it here. So one is 2 microfarad, so another one is 1 microfarad. So in this situation, so 2 microfarad, so another one is 1 microfarad, 2 into 1 divided by 2 plus 1, 2 by 3 microfarad. So look at here, so this 2 by 3 is again it is less than 1 here. So in case of series combination, if you connect the two or more capacitors in series combination, effective capacitance value is always less than the individual or it is equal to individual value. Sometimes if you consider that same capacitance value here, 2 microfarad and 2 microfarad each, 2 into 2 divided by 2 plus 2, 4 by 4. So again, so look at here, its value is 1 microfarad. So if you connect 2 microfarad and 2 microfarad in a series combination, its effective capacitance value is less than the individual capacitance value is how much? 2 microfarad. If you connect these two capacitance in a series combination, so effective capacitance is less than 2 here. So in case of series combination, I would like to believe that in case of series capacitance, effective capacitance is always less than the individual, or it is equal to individual, or it is less than the individual. So what's the conclusion I get it here? In case of series capacitance, effective capacitance is equal to individual or less than the individual. Its value does not exceeds that individual capacitance value. For example, 2 capacitance or whatever the value you try, 3 capacitance. So 2 microfarad and 3 microfarad capacitors are connected in series combination. So its effective capacitance will be less than 2 microfarad only. So it means that effective capacitance is always less than the individual capacitance. So in case of series grouping, what are the points I need to remember here? In case of series combination, first point I need to remember. What's the point I need to remember here? In case of series combination, charge is remains same. What is the first point I need to remember in case of series combination? So what are the points I need to remember here? In case of series combination, charge is remains same. Charge is remains same here. So in case of series combination, charge is remains same. So what about the potential difference here? Total potential difference is equal to sum of the individual. Total potential difference is equal to sum of individual. Okay. Third point, effective capacitance is always less than or equal to individual capacitance. So this is important one. Effective capacitance is less than the individual, or equal to individual, it should not be greater than the individual capacitance value in series combination. So In case of series combination, I said total potential difference is equal to sum of the individual. Now let me consider that what is the branch potential difference. So in numerical they will ask the question. So what is the potential difference across first capacitor and what is the potential difference across a second capacitor. For example, if I am supplying that 5 volt voltage here, what is the total potential difference here? Total potential difference is 5 volt. So one is 2 microfarad, another one is 3 microfarad. Capacitors are connected in a series combination. What about the potential in the first capacitor and what about the potential in the second capacitor I need to determine. So in order to understand such thing, I want to get that branch potential difference formula here. So in order to get that branch potential difference, so I will derive that equation for branch potential difference in case of series combination. So look at here, in case of series combination, so total potential difference is equal to sum of the individual, I said. So what about the formula to determine the branch potential difference? Branch potential difference here. So in series combination, which of the quantity will be remain same, I said? So charge is remain same. So Q1 is equal to Q2 here. So which quantity is remain same here? Charge is remain same. So total potential difference is equal to sum of the individual. So look at here, total potential difference is equal to sum of the individual. Sum of the individual. Shall I take that V is equal to V1 plus of V2 here? So V is equal to what? V1 plus of V2. Now, so I will rearrange this one. So V1, shall I take this one as V1 is equal to what? C1 by Q1 here. Sorry. So V1 is equal to Q1 by C1 and V2 is equal to what? Q2 divided by C2. Then equation 2 I will rearrange here. So V is equal to V1. So V1 is nothing but a Q1 by C1, Q2 divided by C2 here. So in case of that series combination, which quantity will be remain same? So charge is remain same. So Q1 is equal to Q2 here. So Q1 is equal to Q2 means Q2 also I will take it as a Q1 here. So look at here, Q divided or Q1 by C1 plus of Q1 by C2. Why? Because charge is remains the same here. So V is equal to Q. 1 divided by C1, 1 by C2 here. V is equal to Q into or Q1 into. Shall I take that LCM here? C1 into C2 divided by C1 plus of C2 here. What's that equation? I get it here. V is equal to Q1 into C1 plus of C2 divided by C1 into C2. Let me take this as a equation 3. So Q1, shall I take it as a C1 into V1, where Q1 is equal to C1 into V1. Then equation 3 becomes, so look at here, so I am substituting that Q1 value here. So Q1 is equal to, shall I write it as a V1 into C1 here? So wherever Q1 is there, so just I will take that C1 into V1 divided by C1 plus of C2 divided by C1 into C2. Here the term C1 will get cancelled out here. So if term C1 is getting cancelled out means I want to determine the branch potential difference here. So that V1 value I need to determine here. So V1 is equal to, shall I write this equation as V into C2, V into C2 divided by C1 plus of C2. Look at here, what is the formula to determine the branch potential difference here? So potential difference across the first capacitor. So that is V1 is equal to V into C2 divided by C1 plus of C2 here. So look at here, V1 is equal to what? V1 is equal to V into C2 divided by C1 plus of C2, where V in the sense total potential difference, C2 means capacitance of the other branch, so divided by C1 plus of C2 means total capacitance. So in generally I can write the formula for branch potential difference here. So look at here, so in case of that branch potential difference in a series combination, So V1 is nothing but a branch potential difference here. Branch potential difference is equal to V means total potential. Total potential into, so branch potential difference is equal to total potential into, so C2 means capacitance of the other branch in the sense, so look at here, so this one C1 and this is C2 connected to battery here. So I want to calculate that what is the potential difference across the first capacitor, so that is branch potential difference, it is equal to total potential difference into capacitance of the other branch. So in this capacitance I need to find out the potential value. So what is the connecting formula? Total potential into capacitance of the other branch here, so that is capacitance of other branch divided by C1 plus of C2 means what? Total capacitance. Total capacitance. So look at here, what is the formula or what is the generalized formula to determine the branch potential difference here? Branch potential difference is equal to, for example, so potential difference across the first capacitor, so that is V1. V1 is equal to total potential difference, that is V, into capacitance of the other branch. So this is the first capacitor, so I want to determine the potential difference across the first capacitor. So for that purpose, branch potential difference into total potential capacitance of the other branch, so other branch means C2, divided by total capacitance C1 plus of C2, or I need to find out that potential difference across the second capacitor. So look at here, I want to get that potential difference across the second capacitor, so that is V2. So V2 is equal to total potential in the sense that is V. Next, capacitance of the other branch. So in order to determine the potential difference across C2, which capacitance I need to consider here? C1, capacitance of the other branch divided by total capacitance C1 plus of C2. So this is the generalized formula for branch potential difference in case of a